Good afternoon, my name is Ahmad Fahmi Haryono and my student ID is 22055311136, and I'm gonna do a presentation about linear equation and matrices. Section 1.1 System of Linear Equation 1.1.1 Introduction to Linear Algebra. We're all familiar with the simple one-line equation. An equation is where two mathematical expressions are defined as being equal. Given 3x equals to 6, we can almost intuitively see that x must equal to 2. However, the solution isn't always this easy to find, and the following example demonstrates how we can extract information embeddedly in more than one line of information. Imagine for a moment that John has both 2 ice cream and 2 drinks for €3. Let x cost of the ice cream and y equals to cost of the drink. Then the problem can be written as 2x plus 2y equals to 3. At this point, it is impossible to find a unique value for the cost of each item. However, you are then told that Jen bought 2 ice cream and 1 drink for 2 and 50 cents. With this additional information, we can model that problem as a system of equations and look for a unique value for the cost of ice cream and drink. The problem can now be written as 2x plus 2y equals to 3 and 2x plus y equals to 2.5. Using a bit of guesswork, we can see that only sensible value for x satisfy both equations. X equal to 1 and y equals to 0.5. So we can conclude the equation. Next, what does the term of linear equation mean? An equation is where two mathematical expressions are defined as being equal. A linear equation is one where all the variables such as x, y, z have index of 1 or 0. Only for example, x plus 2y plus z equals to 5 is a linear equation. The following are also linear equations. X equal to 3, x plus 2y equals to 5, 3x plus y plus z plus w is equal to minus 8. But the following are not linear equations. For example, x cubed minus 1 equals to 0 because the index of the variable x is 2. So this is actually a quadratic equation. Linear algebra is a systematic exploration of linear equations and related to some kind of arithmetic called the arithmetic of matrices, which we will discuss later in this chapter. However, linear algebra isn't exclusively about solving about linear system. The tool of matrices and vectors have a whole wealth of application in the fields of functional analysis and quantum mechanics, where inner product space are important. Other applications include optimization and approximation, where the critical question are. 1.1.2 System of linear equation. We can plot linear equation on a graph. Like this photo, show the example of two linear equations. They are straight lines in two-dimensional and plane in 3D. This is why they are called linear equations, and the study of such equation is called linear algebra. Generally, an infinite number of linear equations with an infinite number of unknown x, y, z, and w is called a system of linear equations, or just a linear system. For example, the following is a linear system of three simultaneous equations with three unknown x, y, and z. X plus 2y minus 3z equals to 3, 2x minus y minus z equals to 11, 3x plus 2y plus z equals to minus 5. Next, solve the equation about the cost of ice cream and drinks algebraic means. 2x plus 2y equals to 3. The first line. The second line is 2x plus y equals to 2.5. The solution is this one with elimination, so we can find the y equation. It's the y is 0.5, so we can substitute to the line 2x plus 2y equals to 3 implies, and we find that y 0.5 and x equals to 1. Next, section 1.2 Gaussian elimination. 1.2.1 Introduction to Matrices. In our introductory example from the previous section, we formed two equations that describe the cost of ice cream x and drinks y. This equation, note the first column values only contains coefficient of x, and the second column only contains coefficient of y. So we can write like this. The bracket on the left contains the coefficient from the problem and is referred to as the matrix of the coefficient. The brackets of the right hand side, this one, contains the total cost in a single column and is referred to a vector. Matrices are used in various fields of engineering, science, and economics to solve real-life problems such as control theory, electrical principles, structural analysis, string theory, quantitative finance, and many others. Problems in these areas can often be written as a set of linear simultaneous equations. It is easier to solve this equation by using matrices. X 1.2.2 Elementary row operation. Suppose we have a general linear system of m equations with n unknown label x1, x2, and x3, and xn given by this one, where can be coefficient b are real numbers and x1, x2, x3, and xn are placeholder for real number that satisfy the equation. The general system can be stored in matrix form as like this. 1.2.3 Gaussian elimination. Gauss, born in 1777 and died in 1855. This is his picture, widely regarded as one of three greatest mathematicians of all time, the other being Archimedes and Newton. By the age of 11, Gauss could prove that 2 square root is irrational. At the age of 18, he constructed a regular 70-sided polygon with a compass and unmarked straight edge only. Gauss went as a student to a world-renowned center of mathematics, Göttingen. Later in life, Gauss took up a post of Göttingen in published papers in number theory, infinite series, algebra, astronomy, and optics. The unit of magnetic induction is named after Gauss. A linear system of equations is solved by carrying out the above elementary row operation 1, 2, and 3 to find values of the unknown x, y, z, and w. This method saves time because we do not need to write about the unknown x, y, z, and w each time. And it's more methodical in general. You will find there is less likelihood of making mistakes by using this Gaussian elimination process. Next, this is the example of Gaussian method, Gaussian elimination process. Next is the continue before. 1.2.4 Extending row operation. The Gaussian elimination process can be extended above example so that the first zero number in this bottom row of star is 1, that is, you can see on my screen. How do we convert 45 per 4 into 1? Multiply the bottom row by 4 like this. Next, section 1.3. As shown in the previous section, matrix notation provides a systematic way of both analyzing and solving linear systems. In section 1.2, we came across a single column matrix that we referred to as a vector. Vector, being the simplest matrices, are also the most frequently used. However, to understand the how and why of matrices, we need to grasp the underlying concept of vector. Vectors are a gateway to comprehending matrices. By analyzing the property of the vector, we shall come to a fuller understanding of matrices in general. Well, what are vectors? In many situations, answering the question how much is enough. Sometimes one needs to know not only how much, but also in which direction. Vectors are the natural type of thing that answers such a question, for the capable of expressing geometry, not just size. Next, 1.3.1 Vectors and scalars. The physical interpretation of a vector is a quantity that size, magnitude, and direction. The instruction walk due north for 5 kilometers can be expressed as a vector. Its magnitude is 5 km and its directional is due north. Velocity, acceleration, force, and displacement are all vectors quantities. The instruction go on 5 km walk, but now vector because it has no direction. All that is specified is the length of the walk, but we don't know where to start or where to end. We shall now start referring to this as a scalar. So what is scalar? A scalar is a number that measures the size of a particular quantity. Length, area, volume, mass, and temperature are all scalar quantities. How do we write down a vector and a scalar, and how can we distinguish between them? A vector from O to A is denoted OA vector, written in bold typeface A, and can be represented geometrically as shown below, like this picture. Next, a scalar is denoted by A, not in bold, so that we can distinguish between vectors and scalar. Two vectors are equivalent if they have the same direction and magnitude. For example, the vectors D and A in a picture below are equivalent, that D equals to E, like this picture. The vectors D and E have the same direction and magnitude, but only differ in position. There are many examples of vectors in the real world. Next, 1.3.2 Vector additional and scalar multiplication. The result of adding two vectors such as A and B in Fig 1.16 in the diagonal of the parallelogram A plus B as shown like this. The multiplication K for a real number K with a vector A is the product the size of A with the number K. For example, 2A is a vector in the same direction as a vector A, but the magnitude is twice as long. This one. Next, 1.3.2 Vectors in R cube. R cube is in the x minus y plane, representing the Cartesian coordinate system named after the French mathematician and philosopher René Descartes. René Descartes was a French philosopher born in 1596. He attended a Jesuit college, and because of his poor health, he was allowed to remain in bed until 11 o'clock in the morning, a habit he continued until his death in 1650. After graduating in 1618, he went to Holland to study mathematics. Here Descartes lived a solitary life, concentrating only mathematics and philosophy. His main contribution to this mathematics was analytical geometry, which include the present x minus y plane and three-dimensional space with x, y, z-axis. The coordinate system cemented algebra with geometry. Prior to the coordinate system, geometry and algebra were two different subjects. In 1649, Descartes left Holland to tutor Queen Christina of Sweden. However, she wanted to study mathematics at dawn, which did not suit Descartes, who never rose before 11 a.m. As a combination of the early starts and the harsh Swedish winter, Descartes died of pneumonia in 1650. Next, 1.3.4 Factors in R cubes. What does the notation R3 means? All are the triples of real numbers and is also called true space. We can extend the vector properties in R-cube mentioned above to 3 dimension. R-cubes pronounced R3. The x minus y plane can be extended to cover 3 dimensions by including a third axis called the z-axis. This axis is at right angle to the others two an x and y axis. The position of a vector of 3 dimensions is given by 3 coordinates x, y, z. For example, the following coordinate 1, 2, and 5 in R cube is represented geometrically in like this. Next, 1.2.5 Factors in Rn. In the 7th century, René Descartes used ordered pairs of real numbers like this to describe vectors in a plane and extended it to order triples of real numbers. To describe vectors in three-dimensional space in the 7th centuries, vectors were defined as geometric objects and there was no geometric interpretation of Rn for n greater than 3 dimensions. However, in the 19th centuries, vectors began to be seen as mathematical objects that can be added, subtracted, and scalar multiplied that allowed us to extend the vector definition. There are many real-life situations where more than 3 variables are involved, for example, weather condition, performance of companies in a stock market, mortality rates in a population. Next, 1.3.6 Introduction to the dot inner product. So far we have looked at two fundamental operations of linear algebra: vector addition and scalar multiplication, vectors in Rn. How do we multiply vector? One way is to take a dot product, which we define next. Let u and v is denoted by u times v is the quantity given by u times v equals to this one. This multiplication is called the dot or inner product of the vectors u and v. Also note that the dot product of the two vectors u and v is obtained by multiplying each component u, g with its corresponding component vj and then adding the result. Next, 1.3.7 Linear combination of vector. Let v1, v2, vn can vector is in Rn and k1 and k2 can be scalar. Then the dot product like this one is a linear combination. The entries in one of the vector is in formula 1.6 is another set of vector v1. So the dot product is a linear combination of vector. The dot products combine the fundamental operations, scalar multiplication, and vector additional by linear combination. Next, section 1.4 by Arithmetic of Matrices. 1.4.1 Matrices Revisited. What does the term matrix mean? A matrix is an array of numbers enclosed in brackets. The numbers in the array are called the entries of the elements of the matrix. The term is the plural of matrix. In this picture is Arthur Cayley. an English lawyer who becomes a mathematician, was the first person to develop matrices as we know them today. He graduated from Trinity College, Cambridge in 1842 and taught there for 4 years. In 1849, he took up the profession of lawyer and worked at the courts of Lincoln Inn in London for 14 years. He returned to mathematics in 1863 and he was appointed professor of pure mathematics at Cambridge, which a substantial decrease in salary, but was nonetheless happy to pursue his interest in mathematics. In 1858, he published the Memoir of Theory of Matrices, which contained the definition of matrix. Cayley thought that matrices were of no practical use whatsoever, just a convenient mathematical notation. He could not have been more wrong. Linear algebra is used today in engineering, science, medicine, statistics, and economics. Next, 1.4.2 Transformation and Scalar Multiplication. Computer graphics are essentially created using high-speed transformation. For example, computer-animated sequence is based on modeling surface of connecting triangles. The computer stores the vertices of the triangle in the memory, and the certain operations such as rotation, translation, reflection, and enlargement are carried out by transformation matrices. In this context, we can apply a transformation matrix in order to perform a functional such as rotation, reflection, translation, as shown in picture below. Rotation, reflection, and translation. Next. 1.4.3 Matrix addition. We can add matrix in the same way that we add vectors. To add or subtract the matrix, we add or subtract the corresponding location in each matrix respectively. For example, 2 with 3, 4 with 5, 9 with 8, 1 with 7, 2 with 3, 4 with 5, 9 with 8, and 1 with 7. Next, 1.4.4 Matrix vector products. Let us reconsider our example of simultaneous equation from section 1.1. We formed two equations that describe the cost of ice cream X and drinks Y. This equation, the matrix time of vector. In order to use this method, we need to define matrix time of vector as a product of row by column. This one. Next. Matrix time matrix. Multiplication of matrices is not quite as straightforward as additional and subtraction, but the method is not too difficult to grasp. However, the matrix multiplication is the most important arithmetic operation. How do we define a matrix times a matrix? This is the example. A with E, B with G, C with E, D with G, and so ever. For example, applying this to the matrices. And this is the final. Next. 1.4.6 Computation of the matrix. We can write the computation of the matrix in compact form. For example, let A and B matrix, then A plus B means add the matrix A and B. The computation to A means multiply every entry of the matrix A by 2. A software package such as MATLAB can be used for computing matrix. In fact, MATLAB is a short matrix laboratory is a very useful tool which can be used to eliminate the drudgery from length calculation. There are many mathematical software packages such as Maple, Mathematica, but MATLAB is particularly useful for linear algebra. MATLAB commands and other details are given on the website. In the present release of MATLAB, the matrices are entered in with square brackets rather than round one. The summary is A matrix is an array of numbers. We can add or subtract matrices of the same size. Scalar multiplicational scales and matrix. Matrix multiplication AB is carried out by multiplying the column vector of the matrix B by the matrix A. AB means that the matrix A acts on each the column or vector of matrix B. That's it for today. Thank you.